So welcome to lecture number 1 in TSTE27, the analog and discrete time integrated circuits. So the focus of this course is indeed 3 parts: analog, discrete time, and integrated. So they have some different implications of this. We're also going to follow from analog up to discrete time and then towards some more integrated combined circuitry or signal processing. So let's start with a quick overview of MOS transistors, or Cmos. In this course, I'm not going to discuss much about the physics behind the transistor. I'm not really keen on that. To be honest, I don't know much about the physical stuff behind the transistor. I don't have that background. And perhaps more, I don't know, importantly or so, is that we will treat the MOS transistor as a building block, as a component associated with a certain set of equations and functionality. That's what we do. We don't really care about the doping level or the, the silicon crystal structure of the transistor in this course. But let's do the background 10 minutes or 7 minutes and spend some time on understanding the transistor here. So we have typically NMOS and we have PMOS. And let's get back all the way to basics. So we have NMOS, we typically indicate with arrows, PMOS and NMOS in this way. Some people use rings and stuff. I don't use that. And sometimes we also write this a little bit quicker, just sort of dash on the source component of the transistor. So this is what we call drain. This is what we call source. This is what we call gate. D, S, and G. We introduce some different voltages and currents associated with the transistor. So I'm going to introduce the drain current ID here. For now, we will not spend too much time on the PMOS. We will find that the PMOS is just a sort of flipping the NMOS from a sort of equation and component point of view. We have a voltage from the gate to the source, VGS. We have a voltage from the drain to the source, VDS. We have a third voltage, which we sometimes are interested in, and that's the bulk connecting here to the transistor with an arrow in here, the bulk. The bulk defines the sort of common reference, common ground, or common environment for the transistor. This transistor might be implemented in a piece of silicon with a certain voltage level associated with it. And what is interesting in the formulas is a voltage from the bulk to the source, which we call VBS. And in this course, there are some exercises or comments here and there about the bulk source voltage, but in general, we sort of omit it for different reasons. One of them is that some processes don't really care about the bulk voltage. And the other thing is we can quite often see that the effect of the bulk voltage is just a sort of constant that affects your transconductance, your gain of your transistor. And then as a sort of good engineer, i.e. lazy engineer, we just sort of embed that constant in the expression and say, we just add a gamma or whatever. And that gamma could, rather than being 1, we could use the bulk source effect and just say gamma is a half or something. And then continue to do the calculation. So it's just overambitious to spend too much time on understanding the effect of this bulk source voltage at the moment. Then what happens here for the transistor? Well, dependent on the voltages and the currents through the transistors, it has different operating regions. So just recapitulate those. We typically say that if VGS is less than VT, a threshold voltage, which is typically related to the material, so it could be for silicon, you might recognize this 0.7 volt threshold. In digital, we call this off. In analog, we call it sub-threshold. And why do we do that? Well, in our world, it's never off. In fact, you can do quite a lot of operations with a transistor in sub-threshold. We will look at those things later. Then we can turn on the transistor by increasing the VGS voltage. Then it's on. And then it has two sort of sub-regions when it's on, dependent on how much voltage we have applied. It typically relates to the VGS voltage and the VDS voltage. So if we apply a large voltage from the drain to the source, we get a big field this direction. If we go from the VGS, we have a big electrical field in that direction. And they have some different implications on the behavior of the transistor. So we recognize that as if VDS is larger than VGS minus VT, then we are in the saturation region. If VDS is less than VGS minus VT, we are in the linear region. So we have sort of three cases here. We will sort of extend these equations just shortly. We will also find out that in analog design, we will typically try to work here in saturation region. We won't do that. We will see that shortly. But at least for hand calculations, we will always assume saturation region if we don't need to be very, very accurate. So let's take a look at some formulas related to that. So sub-threshold, VGS is less than VT. And now we start to become lazy engineers. So I will introduce a new variable, which I call VF. And that's equal to VGS minus VT. And I will also say that sometimes I will use the notation delta V. And then I say that if VF is less than 0, i.e. off or sub-threshold, then the drain current can be written in this way. So we can write the drain current as some constant I naught times e to the something. And this you recognize as the diode formula. Diode formula. Okay. Then we have another case. VF is now larger than 0, so we have turned on the transistor. But we also say then that VDS is larger than delta V or VF. And then we are in the linear region, and then we have that ID is approximately equal to constant alpha times VF or delta V. Alpha delta V squared. We will shortly look at that alpha. I'm just going to conclude here before the break. So diode formula or this equation. We can also require VF is larger than 0, but VDS is less than, let's type VF here to avoid confusion. VDS is now smaller than VF. and that is the linear region then. And then we have that ID is approximately equal to alpha 2 VDS times VF minus VDS squared. So this is the sort of classical set of equations. Let's just look at that. If I write the diagram like this, and then I put VGS here on this axis, and I put VDS on this axis, and then I put VT here, and then I have sort of demarcation zone here, and I also have a demarcation here. This is now VGS minus VT here. Okay, so we have sort of three operating regions. We have off, we have linear, we have, sorry, we don't have linear, we have saturation here, we have linear here. And if you look at it, in the old days, when we used to have really high voltage, then VT was very small compared to the supply voltage or the voltage range available. And it was sort of easy to design a very high voltage being distinctly far away from VT. So you could sort of operate here in the old days, put your transistor really off. Same here within these boundaries. It was sort of easy to design your transistor to operate with high VDS compared to VT and compared to VGS sort of. So you could operate your transistor distinctly in the saturation region. Or same argument, you could put your operating region here, VGS, VDS, far away from each other and really turn your transistor into the linear region. That's not the case today. So the case today is more or less that we circle around down here somewhere today. And why is that? Well, today VT might be 400 millivolts or something, but the supply voltage is 800 millivolts or something, 0.8 volts. So we are sort of floating around here in the operating regions. So dependent on the signal levels, it might sometimes be in linear region, it might sometimes be in saturation, it might sometimes be in sub-threshold region. That implies that you as a designer today, you don't really know which formula to use. You are sort of always wrong, to be sort of honest. So the solution to that, once again, is to become the lazy engineer and just pick one. So we sort of pick the saturation region because it has quite nice formulas. And it gives you guidelines. It indicates these hand calculations will by design be incorrect due to this argument, but it will from this be able to derive certain directions. You might, okay, I want to increase a parameter to increase the gain, or I want to, do some whatever I want to do. And then you have to go to the simulator as soon as possible. So that's the implication of this figure, more or less. So we can happily do the calculations here, but you can quite soon throw them in the bin. But at least it gives you directions. And then you have to verify in the simulator and be very extensive test cases for this simulator to sort of demonstrate the behavior here. All right, we're getting close to the break. All right, so the outcome was that we would look at the saturation region, this formula, this very simple formula, to be honest. It's just a current equal a constant times some voltage squared. We appreciate or observe that we will be running around in many different operating regions here, and there is obviously some sort of soft combination of these three equations. These three equations were the old extreme ones, far off on the edges here. And They have been with us for the last 40 years. And they will continue to be that, just because this is sort of easier to work with. But once again, going to simulate. So we need to add up some more details to this. It's called second order effects. Of the transistor, and we only care about saturation region for time being. So sat region, and we had ID, drain current, is equal to alpha, and then now I'm going to use delta V squared, even though I'm going to probably write VF now and then also. What's alpha? Well, that's a material constant and a physical constant. So that's equal to mu naught Cox divided by 2 times W over L times delta V squared. Mu naught is the mobility of the charge carriers in your device. So if it's NMOS, it's the mobility of the electrons. If it's PMOS, it's the mobility of the holes. Cox is the capacitance, gate to source capacitance of a transistor. It indicates more or less how strong the connection is. If we, just for the fun of it, do some sort of pseudo-physical description of a transistor like this. The gate capacitance is between the gate and the source. So if you see at the wires here, that's more or less a cap here. So the stronger connection I have here, the more current I'm going to pull. So Cox here, and WL is the width and length of the transistor, physical description of the transistor. The wider I make it, the more current I can push in for a certain voltage because it's wider. The longer it is, the less current, because it's going to be, you know, a long distance from drain to source of your transistor. Once again, if you want to read up on the physical descriptions, that's well explained in the book, and there's no point in doing it here. We sometimes refer to this as S, as in size of the transistor. But conceptually, for me as a designer, I probably don't have any good handles to change the value of mu naught and Cox. They're typically given by the process. But W and L I can design as a designer. I can change them. I can make whatever W I want to a certain limit, of course, and same with L. So that's a fixed parameter. That's a, you know, a flexible parameter or an adjustable parameter. But if you look at this equation, I don't really care. WL, blah, 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 whatever. For me, it's just the parameter alpha. This is my adjustable parameter, so my physical adjustable parameter. So what I'm saying as a design engineer is I have something, I have a handle here with which I can control the current linearly. That's all I need to know. And then I can, with my simulator, adjust that alpha. It's no need to do all this other stuff here. It's just a waste of ink, more or less, in your pen. All right, so with that said, so that's the explanation of alpha. Second order effects, there is some boring thing here. If you look at this device, the transistor, ID is equal to something times the voltage from the gate to the source. So if we just draw it like this, for example, that's a transistor, and that's effectively an amplifier. So if you compare that, that's more or less a amplifier like this. And maybe if we want to, we could have a sort of reference here. So I'm going to put a voltage here, and I'm going to amplify it to a current in this particular case. So the transistor is a transconductance amplifier, is the nomenclature. Transconductance amplifier. So from volt to amps then. And what do we want with amplifiers? Well, we want them to be independent. The gain of the amplifier should be independent of the output voltage. I mean, it's a buffer. So it shouldn't really depend on itself at the output. It should only depend on the input. That's the sort of basic definition of an amplifier. Otherwise, it becomes nonlinear. It becomes sort of, yeah, you get some sort of even memory effects. For an ideal amplifier, you want the output to be independent of itself. It should just be dependent on the input. That's what we have here. We have I equal to some parameter times the input voltage, delta V. So in this scenario, it looks really good as an amplifier. It even have a square here, so we have quite, square gain even. But in reality, we have a limitation due to this field that I told you about earlier. If I have a high voltage from VDS, then I get a big electrical field in a sort of wrong direction. Here I have the field that controls the device in this direction. Here I get another field which sort of distorts the electrons or the charge that moves around in the semiconductor. So what I can do here, or the model, is that a more accurate model, which we typically have to use for our calculation, is alpha delta V squared times 1 plus VDS divided by V theta. Sometimes this is the early voltage, sometimes we typically see this as alpha delta V squared 1 plus lambda VDS. And then this lambda is called the channel length modulation. And the modulation is due to these effects of these electrical fields, then that I get the channel which behaves a bit odd in this transistor. But we typically have to use this parameter to understand a little bit more about transistor. So let's continue and build up some framework around this. And yeah, so the question was the constant alpha. Yeah, I think this was explained here then in the text. Question on the chat there. So let's clarify that for the question then. So just to alpha is equal to mu naught Cox divided by 2 times WL. So just to answer the question on the chat there. Right, so let's do our first amplifier. So we have already actually said that we had an amplifier in the transistor itself. So in some sense, this is already an amplifier, but I have to take care of that voltage, that current coming out there. So what we do is typically to connect that to a resistor, or L, and then I take my output voltage V out here, and I put my input voltage V in here. And here I have a voltage to voltage amplifier. So this RL only acts as a volt to current converter, more or less. So it just absorbs the drain voltage and creates a voltage at the output. So let's look a little bit at the transfer function here. I want to analyze this circuit as a function of V in. So I want to perhaps plot V out as a function of V out as a function of V in. And I want to find out the gain of my device and my operating regions of my device. So let's just make it easy for ourselves and assume this operates in the saturation region. So assume SAT region. All right. So what? Well, it's just Ohm's law, more or less. So we haven't written that especially here, but VDD at the top and ground at the bottom. That's my way of writing it. So if I have just like a dash or a line up here and a line down there, it's sort of assumed to be VDD and ground. And if you don't write anything else, ground is always assumed to be 0 volts. So this current ID, we can calculate. So what do we have? We have essentially KVL, Kirchhoff's voltage law. So we just do plus VDD, go a trip around here, plus VDD minus RL times ID minus VDS. And VDS is nothing else than V out minus ground. So V out then equal to naught. KVL. And ID, we have an expression for from the previous page. So we have, let's reorder this. So V out is equal to VDD minus RL times the alpha times V in minus VT squared here. So alpha is a parameter and VT is this threshold, which we didn't explicitly say, but VT, we typically assume something like 400 millivolts or so. It's typically a constant. Right? So sorry. So V out, we can write this way, and we typically have some sort of square law operation here. There's no point in spelling this out further. We could obviously expand the parentheses here, blah, blah, blah. But we can start sketching. We see that if V in is equal to VT, this term is 0. And then this whole enchilada is 0. And V out is equal to VDD. So we obviously have our breakpoint at VT here. And it claims to be equal to VDD at that point. Okay. And then here it's going to decrease with some sort of square law equation. We are sketching at this point. We obviously see that if V in is too large, if this is 1000 mega gigavolts, this expression would force V out to be also minus megavolts. And that can't really happen. We have 0 to VDD to adjust ourselves to. So obviously VDD can never be less than 0. So there's obviously some saturation going on here at some point. And yeah, we can sort of use the assumption that it's in saturation region here in the middle, and then we realize it's going to limit itself to VDD here, according to this expression. And we can also realize that it's going to limit itself to 0 somewhere here. So obviously some, I don't know, assumption could be this type of equation or expression. In reality, there's obviously a sort of softer transition between all these points. All right, and where do we want to operate on this transistor? Where do we want to put our input signal? Well, this is an amplifier, and assume this is some audio amplifier. We would like to maybe be able to swing the output voltage as much as possible from 0 to VDD. It should jump around like this. V in, we don't really care. It could be a low swing on V in because we know we're going to amplify the signal, but at least we want the output to have as high swing as possible. So one typical approach is to put the operating region approximately at VDD half here. So I want to go out here and I want to pick a V in which locates itself here and creates a VDD half center point at the output. And then if I add a small sinusoid here on the input, I expect to get the big sinusoid at the output, for example. That's the purpose of the amplifier. Now, what you will find as an analog designer is that this point is actually not optimum from a gain point of view. It's optimum perhaps from a swing point of view, up and down, but it will not give you the highest gain. There are other requirements for that. So that's another type of trade-off that we can do. Operating regions and these kind of things is also well covered in the book and the basic courses, but we're going to dig down into concepts of how calculating this operating point and the gain for that point. So let's just get to that idea by looking at this equation. So for this one, it's pretty simple to solve V out. It's straightforward. It's VDD minus this expression. So I could find some expression as function of V in. In fact, I could define the gain A is equal to, and then I have to take the derivative dV out, dV in. That's the slope of this guy. That's my linearized gain of my amplifier. So that derivative is minus 2 RL times alpha times V in at the operating point Q minus VT. So that gives me an expression of the gain, which is pretty easy to handle. But assume now we start adding non-linearities, or these second order effects that we discussed. So let's assume now that V out instead is equal to VDD minus RL alpha, and now I use the delta V because I'm a lazy engineer. And then here we introduce 1 plus lambda VDS, which is V out. Okay, now we see it's a little bit more tricky. It's not difficult to solve this, but I would have to bring out V out lambda to the other side, and I would get the delta V squared also on the left-hand side of the equation. I have to divide both sides, and I will get some sort of expression which is delta V squared divided by something delta V squared. I have to take the derivative of that, and blah. So you will find out that it's very quickly gets into, it's not difficult, it's not, it's not rocket science math, but it's for us, for our purpose, when we already know that we're operating in a very incorrect region, or vague description of the region, and also these equations are all approximate. There is no point in doing this too accurate. It doesn't make sense to use super accurate hand calculation formulas with the assumption already that we have done something wrong. So instead we have to sort of leave this, just look at it as a sketch and sort of look at the trends. What can we tell here? Well, we can tell it's a negative slope, for example. If I've drawn it a little bit more accurate, I would see that I have a higher gain towards the top here. A more accurate drawing of this would perhaps be something like this. So we have high derivative here rather than here. So those kind of things we can see from these formulas, but nothing more really. So let's take it one step further. I'm getting into action. So small signal schematic. Let's derive some important parameters for our purpose. Once again, this is repetition for a few of you. So small signal schematic, what do? I take a look at my transistor like this. drain, source, gate. And then I acknowledge that this is nonlinear. There is a delta V squared term. There is this 1 plus lambda VDS term, etc., etc. So it's not super large polynomials, but it's large enough to make it annoying for us. So what I say instead is that I use Taylor expansion. So if I take f of x, that's equal to f of x naught plus x minus x naught times f prime of x naught, for example, plus a few other components here, or an infinite amount of components, but we assume them to be small. And then I see, if I look at this equation, this is sort of my DC point, and this is my AC point, and this is my derivative, which is the slope, with respect to a lot of different parameters, then both time and different parameters. So I can split my system into a DC analysis, which is my operating point analysis, and an AC analysis, which is my small signal analysis. This is linear, so I still don't capture the nonlinear effects in a transistor. For that purpose, I have to be more accurate. That's very tedious by hand, and typically we relate to the transistor simulator instead. But at least taking these two steps at least helps us to understand a little bit more once again about these directions. What can I increase to increase gain, or what can I sort of decrease to improve the swing, or something like that? What can we read out from these equations? So the equivalence here is that this guy, a transistor, I can replace in the equivalent small signal schematic with a component which has nothing connected to the gate. It has a current source, and it has a current source like this. And that's my drain, that's my source, and that's my gate. And these are linearizations. That's the derivative here with respect to the different parameters. So this guy is the one we call GM, which you might recognize. So that's the variance in current, dID, as a function of dVGS. So the derivative of my expression. This guy is the one we call GDS, which is equal to dID dVDS. So let's just recapture that also in this first introductory lecture. So it defines the linearized amplification of the input voltage, and this the linearized gain of the amplification of the current with respect to the output voltage. So here we have GM times VGS, and here we have VDS times VDS at the output. One can notice that GDS times VDS is a current source which is dependent on the voltage across itself, and that's nothing else than a resistor or a conductor. And this guy is a current source as per that. So let's look a little bit on these definitions, and then we'll boil down to a compact model shortly and wrap that up. So GM, dID VGS, well, we already know that ID is equal to alpha delta V squared. And delta V is equal to VGS minus VT. But if we look from a derivative point of view, we see that according to the chain rule, d delta V, dVGS is equal to 1. So I can sort of replace this dID dVGS in a clever way. I can do dID d delta V times d delta V dVGS. And I know that this term is 1. So dID dVGS is equal to dI dV dd, d delta V, sorry. So Gm, I can just derive this expression with respect to delta V. So that means that Gm is equal to 2 alpha delta V. Delta V is the operating point voltage. We will come back to that, but I'll write it like this for now, just to get to some conclusions. Here, we can rewrite this as simple as squaring delta V and dividing by delta V. And then we see that up here in the Taylor, in the well, we don't have any Taylor expansion here, but up in the numerator here we have the original ID expression times the 2. So this is equal to 2 ID operating point Q divided by delta V Q operating point. We can also write this as the following manner. If I have Gm is equal to 2 alpha delta V, which was the original, I can write this as 2 times the square root of alpha times the square root of alpha times the square root of delta V squared. And then you see we find also IQ here, this part. So this is equal to 2 square root of alpha times square root of IDQ, if you like. All right. What about GDS? Well, then we have to go back to this equation. We have a lambda here, we have a VDS. So we can take the derivative of the current with respect to VDS. So that gives us that GDS is equal to alpha delta V squared times lambda. And then as engineers, we make it a little bit easier for us. We say that this is approximately equal to alpha delta V squared 1 plus lambda VDS times lambda. So that's then equal to lambda IDQ. So we have some various ways of writing this. We have a GM, which is this one, which we're going to use quite frequently in this course, 2 IDQ divided by delta VQ. And this guy, GDS, is equal to lambda IDQ. So let's see how we can use that and compile this page. All right, so we said that a transistor linearized using Taylor expansion can be written like this, and then use a conductor instead of a current source at the output, like this. Drain, source, gate. And this is now GM times VGS, and this is GDS here. And we know now that GM is equal to 2 IDQ divided by delta V Q. We're shortly going to omit these Q's, and we will just assume that it's understood by the context what these values are. So this Q is just wasting ink, but we leave them there for now. And GDS is equal to lambda IDQ. So, and as you might have noted, sometimes we see the bulk effect here also added as a current source. But if one does the maths, one will see that the bulk source typically boils down to something which gives you the same type of numbers as the GM times VGS. So we just assume there is a constant in front of these equations. So we just omit it for now. All right. So what about the gain of the transistor? Now we say voltage gain here, voltage gain of the transistor. Well, we can look at the small signal. We have Ohm's law here. This is a Norton equivalent, current source parallel with conductor. So VGS over VDS, sorry, VDS over VGS. So gain is equal to VDS divided by VGS. And that's equal to, there's nothing connecting here, so it's all defined by the right-hand side of the diagram. So first of all, the current is pointing in the wrong direction, so we have the minus. And then it says GM times VGS divided by VGS. And then times the resistance, so this should be times 1 over GDS then, to get it to the right. So VGS disappears. This is now equal to minus GM over GDS. And using these two equations and put them together, 2ID. Now I omit the Q, delta V divided by lambda ID. And then also here we see we can cancel ID against each other. So the gain is thus equal to minus 2 divided by lambda delta V. Right. So an important conclusion here is that the current, it's there indirectly, but it's not obvious in the formula. Instead, the delta voltage is obviously in the formula, which implies that the gain is the highest when you pick the smallest delta V. So that means if we go back to our amplifier here, I get the highest gain when I put myself as close as possible to this VT edge here. So I really have to push down my input voltage towards ground here, towards the threshold voltage, then I get the highest gain. And as you notice, then that really contradicts this decision here to some extent. It's not the whole truth, but it's a sort of part of the truth. The truth is a little bit hidden in the way I've drawn the diagram here, but there is a slight contradiction here at least. That's the result. So we have a quite simple way of defining gain of a transistor. I never note, so lambda here, that's 1 over the early voltage, V theta. One can also show that this is inversely proportional to 1 over the channel length for information. So if I want to increase my gain, I could also choose to increase my L here. That would also increase this expression here. So I have 2 divided by lambda times delta V. So either I decrease delta V and A increases, or I increase the L, the lambda decreases, and then this whole enchilada increases. So I have certain ways to fix this physically or electrically to change the gain. All right, let's get to the intended wrap up of the lecture today. So we're speeding on here, so if there is something which goes too fast, just throw in some questions or go through the YouTube video afterwards and throw us questions on the Teams channel. But yeah, introductory material to get up to speed before lecture 2, when we will start using all these expressions more freely. We're already at a quite high level here. All right, so let's just look at this amplifier here, like we did in the beginning. So we had some ways here to derive the gain. So let's just do that with small signal schematics at the moment to repeat that. RL, have V out, V in, and small signal, equivalent small signal schematic of this one. So I already assume I found an operating point where I locate my voltages and currents. And then I use Taylor's theorem or Taylor's approach to linearize this. So for example, we know that VDD, if we derive a constant voltage with respect to something, it's going to give us 0. So all constant voltages are just forced down to 0. So equivalent small signal schematic would be something like this. RL, and then I would have my current source and my GDS of my transistor, and V in would just be here somewhere, and this is V out, GDS, GM times V in. And in my linearized world, I don't need to care about VT here, then that's already derived. Becomes 0 when I do my derivation. All right, okay, so obviously this is equivalent to current source and then GDS in parallel with RL, like this. And I'm deliberately a bit sloppy here, showing, not typing out really what's ground, etc. I just assume straight lines in the bottom, that's ground, and etc. So this is sort of back of the envelope writing. So that's what we're going to do throughout the lectures. GM times V in. And let's just do the calculations. So this is RL, and that's 1 over GDS then if we talk about resistors. And sorry, impedance, conductance versus resistance. All right, so V out is equal to minus GM times V in, the current source, times the load, and yeah, either RL plus 1 over GDS in parallel, or just in conductance is GL plus GDS, like this, and GL then is equal to 1 over RL. So that's another conclusion in this course, that we will use inductance, conductances to a large extent. All right, what can we say here? Well, GDS is a parameter which is small. The transistor is a good component, so it has high output impedance. So this GDS becomes low. GL is a resistor, which is typically in the kilo ohm region. Why is it in kilo ohm? Well, we don't know for sure, but if I have kilo ohms, I will get milliamps, which is a considerably okay current. If I have mega ohms for the resistor, to get high output impedance, but then I can't guarantee high current here. If this mega ohm, and we have say 1 volt across this device, I will get 1 volt divided by 1 mega ohm. I can only push out microamps to the output. So it doesn't make sense to have too large RLs. So we can assume that RL is pretty low value, which makes GL large compared to GDS. GDS is thus small, much smaller than GL. So let's look at that. So that gives us minus GM times V in times GL. Sorry, I should have divided by, my excuse. Divided by. All right. And then that's equal to minus GM times RL times V in. And GM we had from the previous paper, 2 IDQ divided by something, for example. Times RL times V in minus etc. But etc. etc. We're not going to go further here, but we see that this expression here is the same as we derived here. So we have 2 RL alpha times delta V, etc. etc. So 2 IDQ, etc. So it's perfectly fine to use also this small signal approach to solve the large signal approach, but the linearized version will be much simpler for more complex circuitry. Okay, so let's just continue preparing for the next lecture by looking at this guy. This guy is evil. We don't really want resistors in our design for many reasons. They are noisy, they are big, they have parasitic capacitance associated with them, and they are just a poor component more or less for our purposes. So let's just wrap up with a final approach, and I will call that active load. I'm going to use a few of your minutes extra, I see on the clock. So active load, I replace the resistor with a Cmos transistor. I connect a bias voltage here. I connect my input voltage, and I connect my load capacitance here also. So I use a transistor as a current source. Why is it a current source? Well, I have a constant voltage. This is a PMOS, so in this case I refer from the top to the gate. So this transistor is designed to give me more or less a constant current feeding the transistor. So it sort of sets the operating point. And let's just derive the gain of this one. And then in the next lecture, we will go through some tables where we compare different types of these building blocks and how we can use them. So I'm going to give 5 minutes extra here. And for you who need to leave, then just look at the video afterwards. So let's do an equivalent small signal schematic of this. And now the nice thing is that the NMOS and PMOS look exactly the same, just with a different reference. So my tip is that you just draw it as they are written. So I have the PMOS on the top, I have my NMOS at the bottom, like this. And then I have my load capacitance, and then we use admittances. So I do SCL here rather. And this I call GN, this I call GP. This is GMN times Vin. This guy becomes 0 because we have V bias to VDD. That's the voltage which doesn't change. So as soon as I derive that, it's going to be 0. So I know that this is GMP minus times 0 then, because VDD minus V bias is a constant, like this. All right, so let's fall down and get to some conclusion. So this guy, we know that this is grounded due to Taylor, and we just fold down everything like this. So I'm just going to write it once here, a bit over ambitious perhaps, but that's GN, GP, and SCL. And this guy is GM times V in, and that's V out. So I'm just doing an intermediate stage here. So this is now equivalent with final drawing. So I have my GM source, and then I can connect all these in parallel according to conductances being in parallel. So another way of using, or why you should use conductances rather than impedances and resistances. GM times V in, GMN, I guess I called it, and V out we have here. Okay, so what you're doing here to some extent is equations, but you do them graphically instead. And that's a quite convenient way of doing it. We will look more into this later in the next lecture or in the seminars, that you actually solve equations. But it's much easier to find the errors when you backtrack a set of pictures rather than a set of equations, is my tip. All right, so let's conclude on this guy. So, number 9. Okay, so we have a, for my sake, I just redraw this here again. GN plus GP, so I'm going to scan these papers and add them to Cmos. And GM and VN. So we have that now we can type A of S as a function of the frequency variable S. That's going to be minus GMN divided by GN plus GP plus SCL. Why A? Well, I said that A is equal to V out divided by V in of S then. All right. So this could be the answer to some extent then. That's my gain of my transistor stage here. But let's just write this on Bode's normal form, BNF. So I'm going to write this as, I'm going to extract this part of the denominator, and then I get this as minus GMN divided by GN plus GP, and then 1 plus S divided by GN plus GP divided by SL. So I'm writing that in a slightly awkward way. But the nice thing now with Bode's normal form here is that we can identify the DC gain directly in the expression and the pole directly here. So that's my DC gain, A0. This is my pole down here, P1. So that's equal to GN plus GP over CL. All right, so let's just get to some graph here in Bode's plot. So I have A0 here, I have P1 here, and then I have my unity gain frequency, omega u g, here at 0 dBs. Okay, let's just conclude here a little bit quickly on my last minute. One can show that A0 is times P1 is approximately equal to omega ug. And this is what we call the gain bandwidth trade-off. Like that. Okay, we don't have more time today. I might add up some extra video just to wrap this up a little bit. But the point is replacing the resistor with a transistor, and it's going to show that you can get higher gain with this. And I didn't reach that far today, but let's continue that next time. So